All right, here's another classic optimization problem. We wish to manufacture a cylindrical can that can hold 2,000 pi centimeters of soup. So I guess we're in the soup making business now. We've gone from herding cats to making soup. We wish to use the minimum amount of material to make this can. What are the dimensions of the can? Okay, minimum amount of material. Okay, what do I mean by amount of material? Well, to make this can, I need to make a top and a bottom and the sides. So I think, maybe I can assume uniform thickness. So maybe the thing that I need is the area. And how do I find the area of this can? Well, the can's made up of three pieces. There's the top, there's the bottom, and there's the sides here. Um, Top and the bottom are circles. So let's see, if I put a radius on this, call that R, right? Uh, so pi times the radius squared would be the area of the bottom. The top would be the same, so I must have two of those. And then I've got the sides. Well, how am I going to do the sides? Well, actually, if you think about it and you slice that side open and unroll it, it actually rolls into a rectangle. The height of the rectangle is whatever the height of the cylinder is, so let's give that a name. Let's call it H. And the length of that rectangle is going to be the distance all the way around the cylinder. Well, that would be the circumference of this circle of radius r. So this must be 2 pi r. So the area here is the length times the width, so 2 pi r h. Right? So there's the thing that I'm trying to minimize, right? Find the minimum amount of material, minimize that area. Notice the things that can change here are the radius and the height. I can have really, sort of tuna fish can looking things, or I could have, ones that look, tall and thin, more like one of those power drinks, highly caffeinated things nowadays. Um, anyway, so the the radius and the height seem to be my variables, okay, and the area is what I'm trying to minimize. Now, there's two variables here, r and h. In a Calc 3 class, we'll actually come back and do these again, and you can do it with both variables in there. It's a different technique. But for now, in Calc 1, we can only do one variable at a time. So there must be a relationship that we haven't used yet between r and h that's going to allow me to get rid of one of them. And there is, in fact, if the soup can is supposed to hold 2,000 pi cubic centimeters. Is that a big can? Is that a little can? Well, a cubic centimeter is the same thing as a milliliter, so 1,000 cubic centimeters are in a liter. So this is like 6 liters, a little more than 6 liters, so a gallon and a half-ish. So kind of a big soup can. This is a Costco variety, I guess. But there's that volume there that we're going to be able to use. The volume is the area of the base times the height. So the area of the base is pi r squared and the height is h. And so I know that that volume has to be 2,000 pi equals pi r squared h. So if I solve for one of them, let's solve for h. H is equal to 2,000, the pi's cancel out, divided by r squared. And then I can plug that in to here to get that my area now is 2 pi r squared plus 2 pi r times h, which is 2,000 over r squared, which I guess I can simplify that a little bit. 2 pi r squared plus 2 pi, the r's cancel out, so I've got sorry, something is not happening like I thought it was going to, but anyway, 4,000 pi over r. Okay. Now I have the area just as a function of r. I'm going to see, are there any minimums or maximums on this radius? Well, certainly the radius can't be any less than 0. Um, and actually, I don't even think it can equal 0. Because if it did equal 0, the volume would be 0, and so I don't have my volume. It could be pretty small, though, and it would just mean that in order to get this much volume, this cylinder would have to be really, really tall. Also, um, I think R could be actually as big as you want, as long as the height, right? R can be arbitrarily big. It just means that the height is going to be really, really small in order to keep the volume correct. So there's really no endpoints here. But I think you can see that, well, at least on the infinity end, as R is getting really big, the area at the top and the bottom are getting huge, and you're using way too much area. What's happening as R is getting small? Well, as R is getting small, this piece is getting small, but this piece is getting big. So now we're at the point where we can take a derivative, set it equal to 0. Look for critical points of this thing, right? So here we go. dA dr is, what's this, 4 pi r plus, actually minus, because this is an r to the negative 1, so minus 4,000 pi times r to the negative 2. Right? So there's the derivative. We're looking for maxes or mins. What are we looking for? Min in this case. So we got to find when it's critical. Critical if the derivative equals 0, or if it's undefined. In fact, there is a place where it's undefined, because when r is 0, this is going to be a problem. But when r is 0, that's really not part of that's not part of the domain we're looking at. So I don't have to worry about r equals 0. I'm just looking at now, when is the derivative equal to 0? So 0 is equal to this thing, 4 pi r minus 4,000 pi over r squared. So solve for r. I've got 4 pi r equals 4,000 pi. Let's see, divided by r, so I'm multiply by r squared. And multiply by r squared and divide by 4 pi. So I've got r cubed is, the pi's cancel out, the force r cubed equals 1,000. Well, that's convenient. R equals 10. So the radius is equal to 10, and the height is 2,000 divided by r squared. So the height is 2,000 divided by 10 squared, which is 2,000 divided by 100, which is 20. So the height is 20 and the radius is 10. Actually, that's interesting, because if this is 10 and this is 10 and the height is 20, essentially this cylinder is just as wide as it is tall. Be interesting to go through your cupboards and check out your cans and see if you have any that when you put them on their side, put one on its side, is it just as tall as it was wide? If you have any that do that, then what they've done is they've minimized the area. Now, how do I know it's a minimum and not a maximum? How do I know? Well, how do I know? Essentially what I'm thinking is I look at the graph of this thing. Sorry, not of this thing. This is the derivative. If I look at the graph of this thing, This is this piece right here is just a parabola, right? This piece right here is you know, a 1 over x kind of thing. Right? Oops, that does not that, but does this, and then you got to add them together. Okay, so the part we're looking at though is from 0 out to infinity. So when they're adding together here, let me to do the graph in red. You know, close to 0, this piece is dominating because the parabola is 0 and the hyperbola here is really big. But then as x gets bigger, the hyperbola comes down to 0 and the parabola gets really big, so it dominates. So in the middle it's doing something like that. With both of them positive, that red curve will always be above both of the blue ones. Right? And so what we did is we found this spot right here where we were at a minimum. So what did we do? Right? We established our objective function. We wanted to minimize the area. We drew a picture and labeled the things that can change with variable names. So the radius could change, the height could change. We used those variables to write our objective function in terms of those variables. We used a relationship between the two variables to just get the objective function in terms of one variable. We checked to see if there are any points, any endpoints, and then we took a derivative, set it equal to 0 to find the critical points because maxes and mins happen at critical points. Okay. There you go. There's your second related rate problem, not related rate, whatever this is. Optimization. There we go.